Thank you very much. Can I have the slides, please? Yes. Okay, here's the title. This is from Joint Work with my postdoc, Jörg Zimmermann. We have seen, where do I point? We have seen many applications, many breakthroughs of artificial intelligence in the past years. And the question is viable. What is the design theory that is underpinning AI technology and AI engineering? Do we have a design theory? I want to take the question a little bit further. Do we have a satisfying foundational theory of AI? And this is what I want to address in this talk. So the main issues are effectiveness and efficiency, taking you from theoretical considerations to practice, basically the two chapters that you see, and I will conclude with a look upon what is going on in science as it relates to the offerings of artificial intelligence. The standard agent framework is my starting point, the sense, compute, act cycle of an agent in an environment. The environment produces percepts for the agent acts on the environment, thus changing it. The percepts may be structured in a little way, in as much as they consist of mere observations and rewards. A special role plays a concept of goal. We set goals for these dynamical systems, agent-environment interactions. And this, of course, is one of the main questions, the alignment of our human goals that we set for such systems and the systems themselves as they begin to fulfill their cycles. The standard learning framework, if I simply dwell on actions that are predictions, is shown here. You have a learning system and an environment, and one way of formalizing or starting to formalize or coming upon a theory is to have the learning system be modeled by a machine, by an algorithm, and the same thing for the environment. So the goal of prediction is to predict what the environment produces. The environment can be modeled as a program on a universal Turing machine. This program produces percepts. These percepts are taken in by the learning system. The learning system tries to work out or guess or predict the next percept by trying to come up with the program that is guiding the environment. So in this standard framework, the predictor, you have a generator-predictor paradigm. The predictor waits until the environment has produced a new output, and vice versa. This waiting upon one another has no specific, at the outset, no specific model of time or complexity. And this is the main point behind the problem of non-effectiveness of this setup, having to do with the halting problem, the undecidability of the halting problem for the Turing machines. So let's look at a simple example. Fundamental problem shown in this example is illustrated by giving the system a finite sequence of bits, like this sequence of 40 bits, and asking the system to come up with the next bit. So this is a difficult question. Even if you look at this, it starts with some similarity of 001, a regularity 001, 00, then comes a 0. not a 1, and so on, and you have some further regularities in this sequence, but still you cannot tell what's really going on. But the system we ask, the learning system is asked to come up with the algorithm behind this sequence. Now, if I told you this sequence goes back to Leibniz, then it may not be such a tremendous help for you to come up with the answer. This is the point. This is the sequence of binary sequence of pi. After the 3-point, the fractional part of pi. And the 41st bit is 1, but of course, you just believe me. Now, it is a lot to ask for machine learning to date to come up with such a basic thing as Leibniz algorithm producing this fraction of pi. So, as a first inroad into this problem, Ray Solomonoff, who was, by the way, a member of the group in 1956 that coined the term artificial intelligence at the Dartmouth conference, he came up with a model of induction that seems somewhat amenable to further foundational mathematical underpinnings. He said, let's focus on Bayesian learning in program space. So we have a Bayesian situation, and we try to learn a program. Programs are run on a universal Turing machine, as you have seen. And the prior probability of a program, which is only just a binary string, is 2 to raise to the power of minus length of that program. So a program that's only 1 bit long has a prior probability of 1/2. Can be 0 or 1. A program that is 2 bits long has a prior probability of 1/4, because you have 4 possible values in 2 bits. But now Solomonoff, this model of Solomonoff ends at the point of non-effectiveness. The posterior distribution that you're interested in, namely predicting the probability of the next percept, is not computable. This has been proved by Solomonoff himself, and the programs, as I had just mentioned, stopping to produce output, they cause the trouble, the undecidability of the halting problem. So one way we came up with to remedy the situation, to take this Solomonoff framework to effectiveness, is to couple the scales, the time scales of the two systems, of the learning framework and the environment. So in real-world situations, you have, of course, such a coupled situation. The predictor is not suspended all the time while the other one is busy, while the environment is busy, and vice versa. So the mechanism that we come up to couple these two universal Turing machines is clockification. A very simple concept. We simply insert clock symbols, clock signals in the way described here. What has been a 0 becomes a 1-0, what has been a 1 becomes a 1-1, and the clock signal is a 0-0. So just in this way, our input sequence becomes a synchronous sequence, and the Turing machines are coupled by constant space differences in space complexity and logarithmic difference in time complexity, so this mechanism remains universal. So as a fundamental result, we prove that given clockification, given this simple extension, effective universal induction is possible. So this is a big step in our view to make the learning framework of Solomonoff effective. So now, from now on, having effectiveness, we can work out efficiency. Before turning to that, let me look at another important problem in connection with machine learning, namely the scientific underpinnings to uncertainty. So all of you know that most people model uncertainty with Kolmogorov probability theory. but the Kolmogorov axioms actually work for probabilities that are real numbers. What about an approach such as Dempster-Shafer that is important for radiological diagnosis, analysis? There you do not have a single real number, but you have a pair, or degrees of belief. Or some people like to model uncertainty with intervals, or maybe complex numbers, or some other structured objects. So what about that? So this raises the question, if you want a foundational theory and you want to encompass all these viable approaches in practice, looking for an axiom system requires coming up with a basic theory for confidence and confidence universes. And here we were able to prove a result, which I show here, which tells us that Kolmogorov probability theory is included, but we can also take care of Dempster-Shafer and other theories that are important in practice, and connect us up to results in algebra. Another question is, do we have a definition of intelligence in artificial intelligence? What do we teach our students? So my colleague Marco Sutta and his PhD student Leg, who now works for DeepMind, they had collected a survey of intelligence definitions, informal definitions, that spell out intelligence as a measure of an agent's ability to achieve goals, I should add, in an automatic fashion in a wide range of environments. So and this can, of course, be taken to a formula. Agent policy pi assigns all possible sequences of percepts an action, and there is a total reward of a policy that simply collects up all the rewards, executing that policy in a given environment mu. So assuming a computable environment like Solomonov, mu, a binary program running on some universal Turing machine, and the prior probability that I just introduced, is a formalization of Occam's razor, actually, that we follow here. We can come up with a simple formula of collecting up all the expected rewards of the policy pi overall, taking overall computable environments. So now, having that, we can turn to efficiency. So we turn to complexity questions, actually. And we find that the typical complexity theory, asymptotic complexity theory that we teach in computer science does not help very much with finite problems. So it simply has to do with the fact that a Turing machine as a reference machine can hide all the details of a complicated computation in a table. So what is a step, what is a time step in the reference machines that help us study efficiency of machine learning in real environments and solve engineering problems? What is a natural reference machine? We have seen a lot of progress in the past years in formal methods, satisfiability solvers, linear program solvers, it's linear programming solvers, convolution technology, linear algebra problems, solving those on high-performance computers. We have seen a lot of development in hardware technology. So our reference machine should be somewhat in the center of a ball enclosing current machines, current technology. And here I am a little bit hand-waving, but Of course, we have studied the topology of machine spaces a lot, defining similarity of machines, etc., defining such distances between machines. So the centroid definition here has some formal meaning. So we want a reasonable correspondence to current computing devices and yet a clean mathematical definition. And one example that I want to show here is iterated Boolean circuits, where we simply have simple kinds of gates and that we iterate. The input vector produces an output vector, and the output vector for the next cycle becomes the input vector. Just want to show you by example. Just look at this simple sequence, 0001, 0001, 0000. We are, I guess, intuitively ready to continue this with a 1. And how would this prediction problem look like for an iterated Boolean circuit? This is a circuit we had come up with the input of 1, 0, 0. And the leftmost bit of the output vector is the prediction. So if I run this, I indeed find the first bit 0, the second bit 0. You cannot follow the computation here so quickly, but maybe you just see that the output vector becomes the input vector for the next round. And indeed, this simple circuit reproduces my sequence all the way to the point where I'm interested in the prediction. And the prediction actually comes out, the calculation, as 1. Now, interestingly, we have not found a circuit of a similar simplicity to produce a 0 as the next output. Interesting. So how do we search in circuit space? How do we come up with such a solution, with such a program at this level? Even for small numbers like 10, an exhaustive search is impossible. So the idea is to get non-trivial results, we combine evolutionary optimization, machine learning, and high-performance computing. And we come back to the AlphaGo method of deep learning, where you have a value network that approximates the value of a position in the game of Go, and a policy network to have the move selection of the next move. These networks are trained in supervised learning, initially with an expert game database, but you all know that in the next phase, AlphaGo 0 had no such database of human expertise, and yet came up with a better solution. So these are breakthroughs of reinforcement learning. Here you see the value network and the policy network, just shown in an example of game states. How do we search in circuit space? Our idea would be to transform this induction problem of coming up with an explanatory circuit into a graph search problem, a reachability problem for graphs, by just taking a similar approach. This is something we propose. Actually, this is ongoing research. To use AlphaGo or AlphaGo 0 style solution in the search in circuit space, where, as you can see, you can add a gate or delete a gate, or you can remove a connection and come to another circuit topology in this way, and you go through the search space shown here for 4 NAND gates as a research incentive to work out. But we think this would be very viable. So in general, what this leads up to is we classify problems into broad problem areas such as convolution, matrix multiplication, linear algebra problems, problems of inversion, so we have the situation of a 3 realms: an application domain, which can be very diverse, and we will see lots of examples. A translator domain, formalizing the application domain into a solver description language, of which we have really a lot of progress. And the solver domain is satisfiability solvers, graph solvers, etc. So what's going on in science, in many realms of science right now, can be depicted in this way. There are science questions are being answered in a breathtaking fashion in many fields, from physics to meteorology to climate research. We see proposals of answers that go back to the use of machine learning methods.
Thank you.
And take the translation into the realm of high-performance computing via solvers. So some of the conclusions, we're still lacking a truly unifying theory of axiomatization of artificial intelligence throughout, although we have made some progress. We still are working on what can be a reference machine beyond Turing machines that helps us with initial complexity questions. And what about cognition with bounded resources? Despite this lack of the ultimate foundational theory, of course, we see the advance of AI has reached a state where ethical questions on impact on society become pressing issues. Here in my last slide, when I moved to the University of Bonn in the end of the 80s, I founded a lab on probabilistic robotics, and there are some major roots of autonomous driving technology that you find there. And here's the MIT Moral Machine Project is one example of an outlook into questions of accountability and fairness. Natural language processing, social bots, social networks, the role of text generation, OpenAI's text generator, GPT-2 is one example, and finally, an important discussion that had been started just recently, a year ago, concerns the use of prediction technology in the courts throughout the US, an example being the compass system that I've shown you.
Thank you. Thank you. Thank you, Armin. Thank you.